To start, we're going to talk about the Earth's magnetosphere and magnetic reconnection. So what we're seeing here is an animation of the sun, and the corona is expanding into interplanetary space. We call that the solar wind, and that carries a portion of the sun's magnetic field. And so when the sun's magnetic field, that portion, when it's southward, when it encounters Earth, it can merge with Earth's magnetic field, carrying plasma and magnetic flux over the polar cap of the Earth, which then packs into the tail of the Earth's magnetic field, where we will get another merging of the magnetic field in the tail and a release of plasma into the inner magnetosphere. And then you can see here we have, this is one of the major drivers of the aurora borealis at Earth. So to talk in a little bit more detail about what this process is, this is something called magnetic reconnection. Essentially, plasmas, when they're extremely highly conducting, can actually carry magnetic fields with their bulk flow. And when plasma is carrying magnetic fields that have an anti-parallel component merge, you can get this sort of X-shaped geometry where the magnetic fields break, reconnect, and then it leads to jetting of plasma away from the reconnection site. And this is a fundamental driver of plasma jets throughout the universe. In the Earth's magnetosphere, it tends to happen when the interplanetary magnetic field is near southward, or at least that's what drives the most activity. So it merges, you can see that the Earth's magnetic field points northward at the day side, and so as the solar wind magnetic field comes in, it reconnects. You get this X-shaped geometry, and the fields are very taut, which means there's a large Maxwell stress, which leads to jetting of plasma and then a carrying of this open magnetic flux over the polar ionosphere, and then into the tail, where this reconnection occurs again, and the field lines move towards Earth, closed, and then swing around to the day side where they'll reconnect again. And this stirs up large-scale plasma convection in the magnetosphere, as well as in the ionosphere and the foot points of these magnetic fields. So magnetic reconnection is what drives a lot of the really strong activity in the magnetosphere, what we usually think of when we think of space weather and geomagnetic storms. However, there are other mechanisms where the solar wind can couple into the magnetosphere. And one of those is something called viscous interaction. So the solar wind is supersonic, it flows towards Earth, and then it decelerates at what we call a bow shock. You can view it as sort of like a big plasma sonic boom. And then you have a region of flow called the magnetosheath that flows around Earth. And as that sheath flows around Earth, Axford and Hines in the 60s have proposed that this could be an alternative method of solar wind magnetosphere coupling. Essentially, like winds blowing over water, the magnetosheath flow kind of blows on the boundary of the Earth's magnetosphere, stirring up flow in what they call a viscous-like interaction. And so that flow goes down the flanks of the magnetosphere towards the tail, and much like stirring a teacup, you end up getting a return flow that goes back towards Earth and flows back down to the day side of the magnetosphere. And we call that convection. And the plasma flow pattern is actually very similar to that one I just showed you, where reconnection is driving it. And one of the interesting things is if this mechanism works, it doesn't even require a magnetic field in the solar wind. It's purely fluid interaction. Now, the question is, what exactly is this viscous interaction? When Axford and Hines proposed this, it was very hand-wavy. And further studies have shown that the main candidate is something called the Kelvin-Helmholtz instability. So the way Kelvin-Helmholtz works is in any fluid where you have a boundary between two fluids at different flow speeds. We call this a flow shear. So you have a slower fluid and a faster fluid. You can start to form ocean-like waves. Essentially, you get gradients in pressure that create these bulges in either direction along the boundary, and then the flow distorts those, and they roll up into these ocean-like waves, and then the instability's growth becomes nonlinear, and the waves start rolling up and rolling up and rolling up, very similar to an ocean wave breaking. And now, in reality, this cartoon picture is a little bit of an oversimplification. So here is a simulation of a Kelvin-Helmholtz instability in plasma. And what you can see is that it's much more complex. Initially it looks like those nice cartoon pictures, but as the instability rolls up, you get secondary Kelvin-Helmholtz instabilities on the edge, you get all sorts of turbulent eddies, and it's almost fractal in nature. And so we call this fractal-like behavior, this chaotic flow, turbulence. And so anytime I talk about turbulence, I like to bring up this famous quote. A lot of people misattribute it to Werner Heisenberg. He pictured here, he said, when I meet God, I'm going to ask him two questions, why relativity and why turbulence? And I really believe he'll have an answer for the first. In all likelihood, it was probably Horace Lamb talking at the Royal Society. And instead of relativity and turbulence, he said quantum electrodynamics and turbulence. But turbulence is something that is very challenging to understand due to its chaotic nature, and we just don't fully understand why it happens. So what exactly is going on in turbulence? So essentially, what you have is you have energy in a flow on a very large scale where it can't dissipate on that scale. And so you start forming vortices that then break up and form smaller scale vortices that we call eddies. You can see these eddies break off, they form even smaller and smaller scales, some of them coalesce and merge, and it's a very chaotic and nonlinear process. And you can see that there are eddies, or these vortices, on all sorts of different scales, and I'll roll through it one more time so you can sort of get a feeling for this. What I'm actually showing here is electric current. This isn't a plasma, and the current actually traces the vorticity really well. And so that's why we're showing it here, because it just lights up whenever there's an eddy. And so you can see eddies at all sorts of different scales. We call that a cascade, when it breaks up into smaller and smaller scales. So how do we characterize a turbulent cascade? Well, typically what happens is we start in the injection of energy, the energy-containing range. And so the Kelvin-Helmholtz instability, that would be when you first start rolling up these vortices. Now, the energy, now often the energy can't fully dissipate at that scale into the flow due to the various viscous and collisional characteristics of your fluid or plasma. And so what happens is, and no one really knows why, and that's sort of why Lamb and Heisenberg had that why turbulence question, you start forming this cascade where the flow breaks up into smaller and smaller vortices or eddies. And during that cascade theory, it's called the Kolmogorov law, has predicted that you will get this sort of k to the minus 5/3 dependence, and that's your wave number. That's 2 pi over your wavelength. So it's a measure of a spatial frequency, essentially. But you get this k to the 5/3 slope in the energy spectrum in space, and then eventually the slope will steepen, and that's what we call the dissipation range. That's finally where the eddies are small enough that some sort of process, in traditional fluids, it's some sort of viscous process, viscous heating. In plasmas, you often have a low enough density that there's very little collisions. So some other process has to heat and accelerate the particles. We often call this the kinetic range. One candidate in plasmas is magnetic reconnection, which I talked about earlier. So here's another video. Again, we're looking at currents, and you can see that often these eddies will collide, and the magnetic fields at the boundaries will reconnect. So you can see all these reconnection events, these sparks or flashes occurring. as the turbulent cascade evolves. And so that is dissipating some of that large-scale flow energy. Now, another thing that can happen is when you start getting down to kinetic scales and you have smaller and smaller currents and the electrons are decoupling from the protons in a plasma, is you can get waves that can send energy away from the system as they propagate away. The waves can also heat particles. And so this occurs in something that we call wave-particle interactions. And so you can have electromagnetic or electrostatic waves that are very important for the energization of particles in a plasma as well as the dissipation of turbulence. And so the way this happens is something we call wave-particle interactions. Essentially, the particles are surfing on the waves. So on the left here, you can imagine your surfer is an electron or a proton, and it encounters a wave, and in this case on the left, it's surfing down the wave. So the particle is gaining kinetic energy as it surfs down the wave, while the wave loses energy. So we say the wave, the electromagnetic or electrostatic wave, becomes damped. On the right here, we have the particle surfing back up the wave, or pumping the wave. And so the surfer is now losing its kinetic energy, while the wave gains energy and increases in amplitude. So we call this damping on the left and growth on the right. Now, in a statistical mechanics view, you essentially have a distribution function of your plasma. This is an example. We can say these are either electrons or protons. For our purpose, it doesn't really matter. And essentially, what you look at is if you have an electromagnetic or electrostatic wave, it will interact with particles moving at velocities near its phase velocity. And so there is a theorem called the Penrose condition that basically says that the growth or damping of the wave depends on the slope of your distribution function. So if the wave is at a point where the distribution function has a negative slope, the waves are providing energy to the particles and the wave becomes damped. If you have a phase velocity in a region with a positive slope, then particles are actually providing energy to the wave, leading to growth. And a way to look at this is plasma distributions want to relax back to Maxwellian. So if you have any bump with a positive slope, it's going to want to dump energy into the wave and turn this into a hotter, wider Maxwellian. Now, don't worry too much about the next slide. If you haven't had a plasma physics or Jackson E&M, this is just going to look like gibberish to you. Essentially what we want to do to find out if a wave is growing or damping analytically is get a dispersion relation. And so we look at the dispersion relation using the susceptibilities of the various plasma populations. So over here, this little bump that's unstable to growth would have a susceptibility, and then this background distribution would have a susceptibility as well. And so we basically find the susceptibilities, and we can represent it with these special functions called Z functions. Don't worry too much about this. I really just wanted to put this here to point out that we can actually solve this numerically, and it's actually a pretty slick way to look at any measured plasma distribution and say, could we have wave growth here? And so I'll play with this. Does someone have a question, Dan?
Yeah, actually, a little bit ago someone asked, when you say chaotic, can turbulence be quantified using parameters normally used in chaos theory?
So, I don't know a lot about chaos theory. Often turbulence is quantified using various forms of statistics and correlations and spectral characteristics, which I'd imagine would be similar since a lot of chaos theory involves nonlinear oscillations and stuff like that, but I wouldn't know off the top of my head.
Okay, and that's all we have for now. If there's more, I'll try to interrupt you when you get to a good breaking spot.
Sure. So now that we've kind of talked about some of the things that can lead to the dynamics of Kelvin-Helmholtz in general in plasma, I'd like to talk about the Kelvin-Helmholtz in Earth. And so both simulations and spacecraft observations have shown it develops at Earth's magnetospheric flanks. So here's that nice little bow shock, the sonic boom. Here's that magnetosheath flowing around the Earth. And then here you can see these nice little waves kind of rolling up and breaking all along the boundary. And so the question is, so we have this Kelvin-Helmholtz instability. It can stir up, this viscous-like flow I talked about. But how else does it couple energy and momentum into the magnetosphere? And there are a couple candidates. There's reconnection, plasma turbulence, like I talked about, which can lead to mixing, and wave-particle interactions, which can lead to diffusion of plasma across and along the magnetic field. And so today I'm going to use data from NASA's Magnetospheric Multiscale MMS mission to kind of look at these phenomena in one of the major, most well-studied Kelvin-Helmholtz events from the mission. So NASA's MMS it was launched in 2015. It was designed to study magnetic reconnection, particle acceleration, and turbulence in the Earth's magnetosphere. So it's very relevant to everything we just talked about in our introduction. It has 4 spacecraft that are flying in a tetrahedral formation. It can get down to 7 kilometers. It's actually in Guinness Book of World Records as the tightest satellite formation ever flown. And it allows us to perform vector calculus calculations on the data. So we can measure divergence and gradient and curl. Additionally, the plasma measurements are really high cadence. You can get full distribution functions of the electrons every 30 milliseconds and of protons every 150 milliseconds. This is more than 10 times faster than the fastest mission before. We also get 8192 samples per second electric and magnetic fields, which let us study waves. So this is ideal for studying the Kelvin-Helmholtz instability. And so one of the exciting things is because we have 4 spacecraft and full distributions and burst mode data, we can actually study fundamental plasma physics. We're not just restricted to studying large-scale geophysical phenomena. So at Earth, if we're looking at the Kelvin-Helmholtz instability, what will end up happening is your MMS spacecraft will kind of be sitting on the flanks, most likely moving in back towards Earth. And as the Kelvin-Helmholtz instability grows, it'll start propagating along the flanks, down the tail, and it'll eventually wash over or pass over the spacecraft. So the spacecraft will be almost stationary with respect to the Kelvin-Helmholtz, and it's just like one vortex after the other flowing past the spacecraft. And here you can kind of see what it would look like in a simulation. Here's dense plasma in the magnetosheet. Here's tenuous plasma more inside the magnetosphere, and it kind of just flows past the satellite. Now here's a simulation of Kelvin-Helmholtz. Again, we're looking at current, as well as magnetic field lines. And what you can see is as the instability develops, and especially as it rolls up and becomes nonlinear, you start to actually have these compressed current sheets that sort of flank the vortices. And you'll see also in the magnetic field normal to the boundary, we'll call that BY, because that's what I have it labeled later. You will actually see these reversals in the magnetic field of these currents, as well as reconnection occurring on these compressed current sheets. So we can actually try to observe this with MMS. So on September 8th, 2015, about a week after commissioning ended on MMS, we saw our first Kelvin-Helmholtz event on the magnetospheric flanks. And so we're going to see a lot of plots like this, so I'll go through each panel so that you're familiar with it. So this is time. Here you can see this lasts about 2.5 hours. The top panel is ion spectrograms. So this is sort of a flux of the energy flux density of protons. Energy is the y-axis, and the color is that flux, so it tells you what the plasma population is like. And then here we have the same thing for electrons. This is the magnitude of the magnetic field in the plasma. This is the vector magnetic field. This is in GSE components. Z is north-south. Y is sort of dawn-dusk, so it's sort of normal to the flanks. So it's normal to the vortices.
Rick, I'm very sorry to interrupt, but I'm afraid I don't see your mouse scrolling on the page. Could you try clicking on the lower right and turning on, for example, your laser pointer and see if that shows up? If you turn that into a laser pointer, does that? Yeah, that's okay. I can see that now.
Yeah.
I'm so sorry.
No worries. It's good to catch that early on.
And when you're ready, we do have another question.
Let's start. Let's go for a question.
And then we can restart your plot. I'm so sorry about that. Yuedeng asks, KHI includes a wide range of multiple scale components. It is a mission impossible to resolve all of them in the modeling. Just wondering, what is the cutoff frequency or wavelength? Below that, an empirical formula is used.
So, I mean, as far as modeling, obviously there are different models that are better for different phenomena. The larger scale processes can be captured by MHD. You really need to start going to particle and cell to get the more fine scale kinetic stuff like reconnection and turbulence. So in the turbulent cascade, you have your first spectral break. You move from your cascade region to your dissipation region at the ion cyclotron frequency, which is roughly going to turn in, which roughly corresponds to the ion gyro radius. So once you get beyond that, you really have to use particle and cell to resolve anything. I hope that answers it.
I think so. It's at least from my point of view.
Okay. So going back to this plot, here we have our ion spectra. Y-axis is energy, then time, and then you have your flux of particles at different energies. So this is your protons and your electrons. By the way, whenever I say ion, that's a space physics kind of jargon thing. We tend to use proton and ions interchangeably unless otherwise specified. So we'll say oxygen ions when we want to talk about that, but when we're talking about protons, we'll often just say ions. So excuse me if I slip that up. So this is magnetic field magnitude. This is magnetic field vector. Again, Z is north-south. Y is dawn-dusk and normal to the vortices. And X is sort of sunward, anti-sunward. This is our bulk velocity in the same coordinate system. This is our proton number density. This is our average proton temperature. This is our total pressure. And then this is our plasma beta. That's the ratio between thermal pressure and magnetic pressure. Magnetic pressure associated with the Maxwell stress. And so what we can see here is on the left, we have very hot ions and electrons, very low density, and very slow speed in the flow. This is essentially in the magnetosphere proper. And then you can see on the right, we have it's a lower temperature distribution with a wide spread. We see that the flow is much faster and anti-sunward. That's negative Vx. We also see higher density. This is that magnetosheath region of shock solar wind. In between is sort of the boundary layer between this magnetosphere and this magnetosheath. And what we can see is that it's a very messy crossing. Over 2 hours, you see we're kind of oscillating in and out of different plasma conditions. And you can see that the density is wiggling. And in the magnetic field, you see this strong fluctuation in that normal component, that By. So if we zoom in, we can see that we get these periodic crossings of the magnetopause boundary between the magnetosheath and the magnetosphere. And we see these continual reversals in the By component, that normal component. If we go back, that is a signature of those compressed current sheets where we might see reconnection. So if we zoom in even further, here is one such reversal in the magnetic field. You can see it goes from positive, which is when we're in a more magnetosphere-like region with lower density, and then it goes to negative when we're in a more magnetosheath-like region. And at the same time, we see a blast in that same component of the protons. And that is a proton jet. That is a signature of magnetic reconnection. And we actually found that the measured speed agrees very well with the theoretical predicted speed for reconnection jets. So this is an example of an ion reconnection jet happening in the Kelvin-Helmholtz. And this can lead to mixing of plasma and diffusion of plasma across the magnetospheric boundary. And so if we want to look at what a reconnection event looks like when we see this jet, essentially here's our satellite constellation. This is from a different missions paper, but it'll look basically the same. So, our satellite kind of crosses over the crest of this wave into this region of diverging flow, which is our reconnection. Here's where the reconnection occurs, and here are those exhaust jets from the reconnection. And so as we fly through, we see this enhanced flow in the component where the magnetic fields are reversing direction. And, in this event, we saw 42 of these periodic current sheets. That means we were flanking, 41, I guess, vortices. And we observed reconnection jets on 22. And this was the first confirmation of reconnection happening in the KHI, and it was the first direct observation of reconnection. We had inferred it before, but this was the first direct observation. And some events we even crossed closer to the center of where the reconnection occurs. We call that the diffusion region, but that's beyond the scope of the current discussion. So this event is actually very early in the development of KHI. I'll show that later. So one of the big questions we had is we're already seeing reconnection. Why? So the next process we want to talk about is, of course, turbulence. Do we see turbulence? So this is an example of a single vortex period. So here we have two of these compressed current sheets, and then this region where the By slowly returns to positive and then reverses back on the other sheet. And in this region, we see lots of fluctuations in proton density. We see fluctuations in proton bulk velocity. It's not a steady flow. We see really violent fluctuations in the electron velocities. We see magnetic fluctuations. Here you can see sort of an RMS sort of dB fluctuation of the magnetic fields. And you see it's really rippling all through here. And we can see fluctuations in the electric field. So in this region between the compressed current sheets, we're in the middle of the vortices, there are a lot of fluctuations. This is a potential sign of turbulence. So let's look at some of those characteristics of turbulence. So here's the spectra. And so this is similar to that cartoon I showed earlier. So we'll go through this a little slowly. So first, we actually see the spectra similar to the theoretical predictions I discussed earlier. We have a region of cascade where we have a slope f to the minus 5/3, which we're assuming the flow is fast enough that the frequency directly correlates to the wave number. And it looks like it agrees with the theoretical predictions. Then right around the ion cyclotron frequency, which is the frequency at which protons will gyrate around the magnetic field, we see a break in the spectrum and it steepens. So this is that kinetic range where the turbulence is getting dissipated. Now, one thing that was surprising is that the electric field actually shows a much different behavior. It actually has two changes in the slope. It has a fairly steep slope in that cascade region, but then as the magnetic field steepens, the electric field gets more shallow. So this is a signature that you're actually dumping energy from the flow into the electric field. And then at this other frequency, this is called the lower hybrid frequency. It's a characteristic frequency in plasmas I don't really want to get into. We see a second break, and finally the electric field is losing energy. Some other interesting features we actually saw in black is the protons. In red are the electron bulk velocity spectra. We actually see they break during the cascade. So the electrons and protons decouple during the cascade, not during the dissipation. That was a surprise for us. And then finally, we see some spikes in the spectra when we decompose our electric field into perpendicular and parallel to the background magnetic field. We see in the parallel a frequency enhancement right here. We think that's due to something called Whistler waves, which is beyond the scope. But then here, around a few hundred hertz, we see a second shallowing where energy is going into the field. And we'll talk about those waves a bit more later. Another thing we see is something called intermittency. So this is where, if you had a laminar flow carrying a magnetic field and there weren't many fluctuations, and you were to take, an increment like, say, 10 kilometers and correlate the field, that increment would, basically the increments would not correlate with each other, and you'd get a nice little Gaussian distribution. When you have turbulent flow, you tend to start having eddies combining, smashing into each other, and you start to actually get these non-Gaussian wings as you get to smaller scales, and we call those intermittent current sheets, intermittency. And so what we can see, if we look at the kurtosis, on larger spatial scales, the kurtosis is very low, and it's essentially Gaussian. But as you get to smaller scales, you get these non-Gaussian wings and growing kurtosis. And we say this is a signature of small-scale currents that could dissipate turbulence through reconnection, heating, or waves. So we see this intermittency occurring in the Kelvin-Helmholtz instability. So that's another mechanism whereby we can couple the solar winds into the magnetosphere. Finally, what about the waves? So here's another example period with KHI. Here we have our compressed current sheets again, those reversals in By. We have this slow rotation in B with lots of turbulence and fluctuations. And one of the things we see, if we look at the electric field, the red is parallel to the background magnetic field, which will be mostly northward. The blue and green are perpendicular, and we see this blast in the electric field right in this turbulent region. We also see a lot of signatures of mixing in the ions. You can see all these different populations. So if we zoom in on these waves, they're very bursty. They are below the ion plasma frequency, which is sort of a fundamental oscillation frequency. If you were to displace an ion plasma and sort of watch it restore and oscillate, it would oscillate at this plasma frequency. These are somewhat consistent with a type of wave we call ion acoustic waves. They're kind of like sound waves that happen in positively charged ions. And one of the questions is, what's driving these waves? So if we when we want to know what's driving the waves, we go and look at the distribution functions. And so you can see on the left we got our proton distributions, and on the right we have our electron distributions. And there are a couple interesting features. First, we have this dispersive injection of ions. So the red are earlier times, the blue are later times. And so you can see that you start seeing this bump on the ions, or this beam, with a very high energy at later times, and then you start getting lower and lower energies at later times. And so what we're seeing, we call this a dispersive injection. This is evidence of perhaps reconnection occurring below the spacecraft. This is parallel and anti-parallel to B. So this would be coming from below the spacecraft, since the magnetic field is mostly northward. And so could these ions be driving the waves? Another thing we notice is that there's actually this cold core in the electrons. This is the first time we've ever been able to actually observe this. We're actually able to control our spacecraft potential well enough to observe really cold electrons. And we see this cold core. As you can see, there's a bite out because we can't quite resolve it perfectly. But those are two features that are going to be interesting. So now we can do dispersion analysis and use that numerical method I mentioned earlier. So in blue, that's our fit to our observed distributions for the electrons and the ions. This is that beam due to the dispersive injection of ions. And then we'll talk about the red and green later. But what we found is that when we tried to model as close to the measured electrons and just had them be flat, then we didn't get any wave growth due to this ion beam jumping in. And you can see that with the red distributions, and this we see damp. So this is growth rate, and the y-axis is Dan Welling's camera is like right in front, so I can't actually see the label, but I believe it's K wave number. And so you can see that the growth rate is always negative. That means the waves are damped. The particles are surfing on the waves, and the wave is losing energy. However, if we can add a big dip in the electrons, which could possibly be generated by things like turbulence, you can actually start to get a positive growth in the waves. And these waves will tend to grow right at about half of the ion plasma frequency, which is, the frequency at which we observe the waves. So if we can create a bite out in the electrons, and combined with this beam injection, this mixing, we can grow the waves. And there are a ton of examples of these all throughout the region. And they're highly variable in amplitude. You can see them in the spectra, but you can't really see them in the electric field oscillations because they're smaller amplitude. And if we look at where these waves occur, if we look parallel to B, so those are particles coming from below, you can see all sorts of beams and populations mixing in when we see these waves. So they seem to overlap with mixing, but the question is, how do we prove this? So, we need to better understand how these waves are generated, and we also need to know what they might do to the Kelvin-Helmholtz. And so to do this, we need to determine where they're most likely to occur in the vortices. And the waves are highly variable in amplitude. We can't really pick it out by eye, so we need to analyze this statistically. So first, we need to say, where are we in the vortices? And the best metric for that is actually to use that normal BY. So you have these periodic compressed currents which flank the vortices, and then in the vortices you have this slow, positive, turbulent rotation in the BY. So if we just do a quick delta BY, where we just look at the change in BY over a 1/16 second time frame, you see we get these bipolar spikes whenever we get the compressed currents. And if we just do the RMS of the B, you can actually see the compressed currents really jump out. So when you have large RMS, you're in the compressed currents. When you have smaller RMS fluctuations, you're seeing those intermittent structures of the turbulence. So that can tell us where we are. So now we need to actually characterize the waves. So what I did is I basically went through the entire Kelvin-Helmholtz interval, the 2 hours, and I basically filtered E parallel between 100 and 1,000 hertz. That was the range when these waves typically occurred. I then calculated the RMS value of these fluctuations using a window width of 0.1 seconds. That gives us several periods in the frequency range we want. And then I looked for when we had enhancements above 5 millivolts per meter. And 5 millivolts per meter gets us well above any background fluctuations in the electric field we might have. So we have several histograms. I didn't label them, but essentially the histograms are those windows where we have enhancements in the RMS power, and the blue is just every window in the interval. So that's sort of our background, what we observe. So let's talk about what we're seeing. So first off, the waves tend to occur at all values of our RMS delta BY. You can see that 70% of them actually occur at fairly low delta BY. And so when we have a large fluctuation in B, that means you're near intermittent structures or currents. And what we see is the waves seem to have no correlation with the presence of currents. They're not current-driven waves. Additionally, if you look at the background BY, we typically were hanging on the sheath side with this mission. And you can see, the background is mostly negative BY. That's where we're more sheath-like. But the waves tend to be closer to zero and more sphere-like. So they're as we're entering a more magnetosphere-like population. We also see that because the temperature is a lot higher. than what we typically observe. And so this suggests that the waves are actually happening right in the middle of the vortices where all this turbulent plasma mixing is occurring. So the waves are probably not due to reconnection or current sheets being driven, but rather due to the turbulent mixing of plasmas. So, so its possible relation to turbulence, as I mentioned, there's that shallowing of the spectrum, and the E, as we're losing energy in the turbulent flow. And so this could be one of the ways we're actually dissipating turbulence in the Kelvin-Helmholtz instability. And so this could be one of the ways we're heating particles and dissipating that large-scale energy. So as a summary, we get these large amplitude waves in the turbulent region. They seem to be a result of mixing, and they could be dissipating turbulence. We did do a quick calculation. It's in the paper that was just published this year. I can share that with anyone who wants it. It looks like they have diffusion along the magnetic field on orders of magnitude comparable to reconnection and other processes. So this is another mechanism where you can get diffusion of plasma, up out of the equatorial plane from the solar wind into the magnetosphere. There are other waves that have been shown to also lead to this diffusion, and so future work should be looking at these waves for other events. So what about other events?
So real quick, we have a question from Dr. Yuedeng again. Electrons can more efficiently damp the waves than ions. Is that a correct statement?
Yes, and actually, so one of the things we found when we were doing our dispersion analysis was that, when you have that ion injection, even though it has a positive slope and looks like it could grow a wave, it essentially, it was getting Landau damped by the electrons, and so your net wave growth was zero. You had to actually modify the electron distribution, creating that fight out in the cold population to actually facilitate the wave growth and prevent the damping of the waves by the electrons. So yes, that is true.
Thank you.
Any other questions? Or
not at this point, no.
Okay. All right. So we only showed one event here, and in fact, a lot of people in the MMS community kind of make fun of people doing the Kelvin-Helmholtz because we've studied that September 8th event to death. And that event, you can see, is actually, so the sun is down below. You can see it's actually very close to the day side of the Earth's magnetosphere. And that is actually very early in the stages of the Kelvin-Helmholtz development. The waves roll up as they move further down the flanks. So as an example, I'll show you two other events, and we're not going to go into anywhere near the amount of detail because we don't have time. But what do things look like further down the flanks? So here are three events, and this is the one I've beaten to death already in this talk. This one is a little closer to the sort of day-night terminator. So that's this one right here. And then this event is way further down the flank on the dawn side. And so you can see each one, we see a periodic boundary crossings. We see these periodic reversals in the magnetic field. So all of them show very similar features. One thing we can do is how rolled up are they? So one way we can find that out is we can look at the tangential velocity and plot it versus ion number density. And the lower density is magnetosphere-like, the higher density is magnetosheath-like. In the event closest to the day side, you can see that we have this linear trend. The low density stuff is pretty much stationary, and then you're basically moving sunward as you get to higher density, and that's just the sheet flow moving down the flanks. But as you start to get nonlinear, you start to have, and your waves roll up, you actually start to get, your lower density magnetosphere plasma flowing anti-sunward as they roll up and the waves start breaking and crashing. As we get further down the flanks, it gets really rolled up. It gets really nonlinear. And so if we look at that intermittency I was talking about, in the first event, this is what we've already shown. You start to get non-Gaussian wings at very small spatial scales, but as it gets rolled up, we actually see you start getting intermittency just everywhere. It's no longer Gaussian anywhere. So are the eddies getting larger in size? We don't really know. And as the Kelvin-Helmholtz grows, the vortices grow as they flow down the flanks. So does that change all of these physical processes we've been studying? And so the question is, who's going to answer that question? There are a lot of more events out there. MMS has been up for 5 years, and we can compare observations with simulations.